Today's problem was submitted by a viewer, and the message sent to me says the following. Hey, yet another somewhat simple problem. Given an integer n, can you construct a graph with n nodes and the floor of n squared over 4 edges without creating a triangle? We consider a triplet of nodes, A, B, C, if there is an edge connecting all 3 nodes pairwise and all of them are unique. So that's the definition of a triangle. Okay. Could you do the same if the amount of edges were the floor of n squared over 4 plus 1? Okay. So I'll start with the first one. We want to make a graph with n nodes, this number of edges, but without a triangle. Can we do that? Anytime I'm given a question like this, I want to at least try and just play around for small values of n and see whether this can be done. And then, a few things might happen. I might see some kind of pattern. I might see some kind of general method of constructing these graphs which will work. Or maybe what will happen is perhaps I can use, if for some value of n such a graph does exist, maybe I can use that graph to add one more node in a particular way that the property is still satisfied. So the first thing I'm going to do is just experiment with a few different values of n. Let's suppose n is equal to 3, then n squared over 4 is equal to 9 over 4, and this rounds down to 2. So there we go. There's a graph with 2 edges, 3 nodes, no triangles. Simple enough. I think 4 should also be quite simple. For n equals 4, well, the floor of n squared over 4 is 4. So we're just going to draw a square. That's a graph with the correct number of nodes and no triangles. I'm going to create a little table here. So we've already done that. Do we get stuck at 5? Let me make sure I did the math right. 25 squared, or 5 squared is 25. So 24 over 4. I need to add 2 more nodes to this without making a triangle. Interesting. So that works, right? I don't think I have a triangle there. Nope. 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 Yeah, that works. Okay, let's try it for 6. 1, 2, 3, 4, 5, 6. Also, what I'm going to try and do is start with this structure. Okay, there we go. So this is the same graph structure as that. I want to see, so I need to add 1 more node, and I need to add 3 more edges. 1, 2, 3. So that worked, but is there a rule here? Is there a rule for how I add Okay, so something I note here. This has 2 nodes coming from it, or edges. This is 2 edges, that is 2 edges. These have 3. And when I add the new point, I want to connect to all the nodes that have only 2 edges. And now they all have 3. Let me go back to the simple case. In going from 4 to 5, it obviously doesn't matter which node I add to first, right? Because of because of the symmetry in this graph. But if I go there, then I have to add to the opposite one. Okay, so I have 6. Let's try 7. What I'm also finding here is, I believe, up to some sort of, I'm not an expert on graph theory, but I suppose there's got to be some kind of notion of isomorphism between graphs. I believe this is the only graph you can make with 5 nodes that satisfies this, because I note that it's the same as this one. And I would imagine this is the only one you can make with 6. I'm not positive about this, but let's see what happens when we try to go up to 7. And again, I'm going to try to start with this graph. Okay, so if I add one more point here, if I connect this to opposite points like that, I have not created a new triangle. The rule seems to be like add edges to points which are not already connected to each other. So when I had 4 and I wanted to add another point, it doesn't matter which one I begin with. So in this case, I drew that edge there. I drew this edge. And then this node is not connected to the one diametrically opposite from it. So we can connect there. And that's guaranteed not to add a new triangle, because I'm connecting one node to multiple nodes who they themselves are not connected. And then in going from 5 to 6, we basically did the same thing, right? We started with our 5 graph, and then, oh no, yeah, we're good. We put this down, and then I note that these 3 nodes are not connected to each other, right? There's no connection there, and so on. And so that doesn't add any triangles. It can't add any triangles. So if I could show that in going from n to n plus 1, how many edges are added? 2, 3, 3, 4, 4, 5. So it appears in each step, we have to add 2 edges. Then we add 3, then we add 3, then we add 4, then we add 4, then we add 5, then we add 5, add 6, add 6. Pretty sure this pattern is going to continue because of the way squares mod 4 work. And there was clearly a bit of a difference in behavior in how moving from an even to an odd number of edges worked. And going from even to odd, the rule was throw down a node, choose any one node, and then all of the nodes not adjacent to that one. And then in moving from odd to even, the rule was throw down a node and connect to all the nodes that have a minimum number of connections already. I'm going to see if that works. So then for 7, we chose any one node. It's arbitrary, but then this node has 3 that are not adjacent to it. Or sorry, there are 2. From this one, there are 2 others not adjacent, there and there. So that allowed us to add 3 edges. Now let's see what happens in trying to move from 7 to 8. I have to add 4 edges, and what I'll notice is that this has 4 coming from it, this has 4 coming from it, and that has 4 coming from it. If I look at the ones that have 3, 1, 2, 3, 4, if I add to those, it'll work. So it appears, and I bet you if I plotted this more reasonably, I bet you what I'm supposed to do here is connect things so I have here 1, 2, 3, I have 8 there. I need another 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's with 8. I bet you I can do this with 10. So with 10, how many do I need? I need 25. I've already got 10 written here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 5 more. 1, 2, 3, 4, 5. There's no triangles in here. How would I prove that this works? If you didn't see what I was doing here, is I basically just kept going around in circles, but I kept skipping a certain number of nodes. So let me do this for 10 again, and I'll explicitly count out the pattern. And I guess what I could also do here maybe is label these. So the first thing I'm doing is just going to connect them all. So that's 10 edges. Now what I'm going to do is start at 1. And I'm going to skip, I'm always going to skip 2. So I'm going to go from 1 to 4, skip 5 and 6, go to 7, skip 8 and 9, go to 10, skip 1 and 2 and go to 3, so on. And now I do the same thing, except instead of skipping 2, I skip 3. So I'll start at 1, and I'll skip 2, 3, and 4. So it takes me 1 to 5, skip 6, 7, 8, skip 10, 1, 2, skip 4, 5, 6, skip 8, 9, 10. And what I see now, for example, is every node has either 4 or 6 edges. And I bet if I throw in an 11th node, if I connect to everything that has 4 edges, I won't make any triangles. How many have only 4 edges? 5, right? 1, 2, 3, 4, 5. So if I connect 2, 3, 4, 5, I haven't created a triangle here. And how many nodes? I needed to add 5 nodes. There's almost a little bit of group theory going on here. In constructing the appropriate graph for an even number of nodes, you connect them in a circle, then connect them by skipping 2, then connect them by skipping 3, and what happens if I try and connect by skipping 4? So 1, skip 2, 3, 4, 5. I'd go down to 6. Does that break something? Does this add a triangle anywhere? No. Oh, yes it does. That becomes a triangle. So we can't add that. Wait a minute. This doesn't work. I have a triangle in here. Let me try this again. Let me go back to 8. So with 8, I need 16. I've already got 8, so I need another 8 to draw here. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Do I have any triangles? I think this works. Oh, you know what? Maybe that's not... How many lines did I just add? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What if instead I do... Well, how many do I need to add? If I remove all these inner ones, I need to add 15 more. That's 5. And now I can do that again by rotating everything. It's another 5. Now I need 5 more. I could connect diametrically opposite points. Does that work? One to 6, 2 to 7, 3 to 8, 4 to 9, 5 to 10. No, this does not work. Because if I connect 1 to 6, it's a triangle. I mean, I've skipped 9. I haven't tried to do it yet for 9. For 9 nodes. Starting with the 8 node, I would need, for my 9th node, if I use the rule I had before, I would just connect, I would choose any one of these nodes here, and then there are 4 nodes not connected to that one, the odd ones, right? 5, 7, and 1. Now I have nodes either have 4 or 5. 5, 4, 5, 4, 5, 4, 5, 4. So if I add my 10th node, just connect to all the ones with only 4, right? Which will be the evens. 8, 2, 6, 4. So is this not, if I try to draw this with 10 points in a circle, what happens? I mean, 1 goes to 2, 3, 4, 5, 6, 7, 8. Interesting. 8 does not go to 9, but it does go to 10. And 10 does not go to 9. So maybe the labeling of the points as I go in the circle, if I can do that here, if I can arrange these points in a circle, it would be with a different ordering. But so now if I put in the 11th point, every node here now has 5. Wait, what? Oh, I'm missing an edge. I need to add one more edge to this. I guess I can add it. I can connect it to 9 itself. Yeah, of course. All of my nodes have 4 or 5, but I forgot about this one. This one has 4. So I should be connecting to all of the evens plus 9 itself. And I don't think that'll add any triangles. It doesn't seem to. Now with 11, and this, now it looks like maybe I could 1, 2, 3, 4, 5, 6, 7, 8, 10, 9, 1. So maybe I could rearrange this into a decagon. Then with the 11th node added, we can just connect to an arbitrary node. I believe the 10 graph must have some kind of symmetry to it so that the rule would still hold. Connect to an arbitrary node, and then connect to all the nodes not connected to 3. So 5 is not connected to 3. 7 is not connected to 3. 10 is not connected to 3. And 1 is not connected to 3. So I just added 5 edges, which is what I was supposed to do. Yeah, this would obviously, if this is in fact the rule or the method by which you construct these graphs, I'm half convinced myself that that you could keep doing this. But of course, some sort of proper proof would be involved. And I think the way, by labeling the nodes and then if n is even, and I'm going to n plus 1, the rule seems to be put down any one arbitrary edge and then connect the new node to all, in fact, introduce the edge which connects n plus 1 to 1, and then it'll also connect n plus 1 to everything not connected to 1, which will be all of the odds. And then if, in going from n plus 1 to n plus 2, you connect n plus 2 to all the evens, but also to n plus 1 itself. That was this connection from 10 to 9. And I'm not experienced with this type of computation in graph theory, but I suppose maybe there's a way of organizing this setup so you keep track of the fact that there are no triangles. I'm not even 100% sure that in the figure I've drawn here that there are no triangles. I'm just assuming that there aren't any. I don't see any. But yeah, I'm not gonna continue with this one much more. I've already spent a long time on this one. It's a cool problem, and I suspect the second part of the problem from the viewer is, could you do the same if the amount of edges were n squared over 4 plus 1? And I'm assuming the answer is certainly not. Something will just break like this. When I was going through these constructions here, I was never able to add one more edge, and I also just realized that in the way that I've drawn this and set up the rule, I have to kind of, if n plus 1 is odd, in the case if n plus 1 is 11, I've connected 11 to 10, but this rule says to connect it to 9. I think that's because something finicky goes on where you might have to relabel the most recently 2 added nodes. Anyway, in doing this method, I was never able to add one more edge. And then I'm assuming that if you were to work out a proof for this thing to show that this thing works, there will be a step where you run out of space. You just can't conclude that something doesn't have any triangles based on a counting argument. I'm not really sure. It's a cool problem though. Way outside of my expertise, as you can see. I'm just sort of trying to do it for more or less arbitrary values of n. But I'll stop here. If I have anything more to say, I'll put it down in the description. Thanks for watching.